Well, hi everybody. Welcome to your first edition of the weekly review and preview. I want to start by saying thank you for a great first week for all of your work. It's been a pleasure to get to know you and get the opportunity to work with you. So this week we focused on two things. Some pre-calc review focusing on particular content that's going to support our work in calculus, as well as estimating instantaneous rate of change. In regards to the pre-calc review, we looked at writing expressions in power form, factoring, the quadratic formula, polyduco. We looked at a little bit of trig and also domain and range. So I'm going to do two quick examples for you here. Remember, in writing in power form, there's usually two steps. We first want to rewrite it instead of the root, just as a power. And then the second step, when necessary, is to move that variable quantity up to the numerator. So if I were going to do this first problem in two steps, I would start by leaving my coefficients exactly where they are. And then right here, I have x. It's raised to a power of 4, so that goes in the numerator of the exponent. And the root is 7, so that would go in the denominator of the exponent. Now my next step, to get everything on the level playing field, I want to have one coefficient, so my coefficient would be -3/5. I bring the variable expression up to the numerator, and I tell everyone that I moved it with that little negative exponent right there. So that would be my final answer. Y equals -3/5 times x to the -4/7. Now, another important review that we will actually need in the next unit is how to divide a polynomial by another polynomial. And in this case, we will often use polyduco to simplify the expression. So in order to do so, we'll start with our divisor on the outside, and then what we have goes on the inside, and we work backwards to find out what our answer is, which will be above on the top. So since I have x cubed here, that would be x squared, because x times x squared is x cubed, which would give me -1x squared here. Looking over, I need 4x squared, and since I'm already 1 in the hole, I'm going to need this to be 5x squared, which helps me figure out that this would be 5x. So I have -5x right here. Since I need 1x here and I'm 5 in the hole, this will have to be 6x, which enables me to figure out that that is 6. And then 6 times -1 is -6, which is exactly what I need. I'm all done here, and I have a remainder of 0. So my final answer for this problem would be what I got up here, which is x squared plus 5x plus 6. So the new concept that we talked about this week, which is our bridge from the mathematics you've done before to calculus, is rate of change. And we said that we're going to use this old tool, rate of change, aka slope, to get a good estimate of instantaneous rate of change. Now remember, it's an estimate because an instant is one moment in time, whereas if we use slope, specifically the slope formula, we are relying on 2 points in time. So though that is not an instant, we are able to estimate it very accurately by using a change in x or a change in time of 0.01. That enables us to get close enough to an instant because our minds, we can't even differentiate between 100th of a second. And so to us, that is basically an instant. Remember, we have different ways of doing this depending on what we're given. When we are given a table with particular values, then we just have to use what we are given. So say they wanted us to estimate the instantaneous rate of change at 3.5. Well then, if all we have is the table, we would do what I refer to as the underestimate, not because it's smaller, but because it's right before 3.5. The overestimate, using the slope formula for both, and then averaging those together. I'll write those down real quickly just so you can see in case you are curious on this example. So as you can see here, if I were going to estimate the instantaneous rate of change using this table, I would use the slope formula twice, both the underestimate and the overestimate, and then I take those two answers and average them together to get my best estimate for instantaneous rate of change. Now that's good, but we can do better when we are given a function. So say you're given the function d of t is equal to 90 minus 80 sine of 1.2 t minus 3. This is where your calculator comes in handy. You can input this into your y equals equation editor, and then you can start your table at whatever value you need. So if we were still looking for an estimate of instantaneous rate of change at 3.5, we could do a table start at 3.5. But the difference being, we're going back. When we have the choice, we want to change an x of 0.01. And so that's what our change in table would be. So we could get values at 3.49, 3.5, and 3.51. Using those corresponding y values, we'll be able to calculate the instantaneous rate of change at 3.5. So now I want to give you a little bit of a preview of next week. And next week's going to be content that is all new to you. We're going to be talking about limits. Now, to try to simplify it, a limit is simply what you would predict a function to do if it followed the pattern that you saw from each side of a particular x value. So let's start by looking at this example right here. Okay, I have this graph. It's a nice smooth curve. I don't know what it is, but that doesn't really matter. Down below, this is the new notation that you're going to see. This LIM stands for limit, and it's asking me to find the limit as x approaches 2. Okay, so what that's saying is as I follow this function and I get closer and closer to the x value of 2, what do I predict the y value to be? Now, since this is a nice smooth function, there's nothing unexpected about it. The limit is going to be exactly the same as the function value. So in this case, the limit of the function as x approaches 2 is 1. Pretty easy, right? Well, it gets a little more complicated. So here's another example. Not as nice of a function. As you can see, this has a hole in the function. So it looks like we have a constant slope. We have a constant slope of 0, and then we have a constant positive slope. And where those two branches come together, we have a hole. Now, again, the limit is what you would predict it to be, not necessarily what it is. So if we were to look at what this function is doing as we get closer and closer to an x value of 3, from the left-hand side, we would predict the y value to be 2. And as we get closer and closer from the right-hand side, we would also predict the y value to be 2. So our limit is 2, even though that's not the function value. Because, again, a limit is what you would predict it to be, not necessarily what it is. So now we're really going to get you thinking. If you look at this new function we have, it has what we call a jump discontinuity at an x value of 2. And that means that at x equals 2, it's like two different branches that happen, and between them there's a jump or a large break. So when we're asked for the limit on this one, as we approach the x value of 2 from the right or from the left-hand side, we would predict the y value to be 3. As we predict the y value as we approach 2 from the right, we would expect the y value to be -1. Now notice those two things don't match. And so since it's not predicting the same thing from both sides, we would say the limit does not exist. Now, there are different questions you could be asked and have an answer for this problem. So let's say it asks you the limit as x approaches 2 from the negative or from the left. What this is saying is what would you predict the y value to be as you come from the left-hand side? So from that side, you would predict the value to be 3. From the right-hand side has a slightly different notation. We put a plus up there, so from the positive direction or from the right. And in this case, the limit as x approaches 2 from the right we would predict the y value to be -1. Okay? So that's where limits get a little more complicated. When we have nice, smooth functions, the limit is exactly what you would expect because it's a nice, easy function without breaks in it. But when we have holes, gaps, and asymptotes, that's when we have to be aware, and we have to see if the left and the right limit are the same. When the left and right limit are the same, then the full limit will exist. If the left and right limit are different, then the full limit will not exist. That's all for our review and preview this week, and I look forward to working with you next week. Thanks for watching, and have a great weekend.